Welcome to the course of Real-Time Embedded System. Today we will talk about control system. This is going to be our lecture number 30. So previously we talked about control system. We talked about open loop control system that was feed forward, and then we talked about closed loop system that was feed backward. We talked about the steps that are needed in order to design the control of the open loop system. So we started out with the model of the system or the plant, then we went to designing a controller, and finally we stopped at analyzing the controller. So today we will talk about the performance of the controller. So let's get started. So in order to determine the performance of the controller, this is our system model equation, that is v of t plus 1 is equal to 0.7 into v of t plus 0.5 p into R naught minus W naught. So this W naught is our disturbance, this R naught is our desired speed, this P is proportional, which we have chosen in the previous case to be 0.6. This V of t is our current speed, and this V of t plus 1 is our next speed. So how we can determine the performance of the controller? Just substitute t equal to 0 in this equation. So if you put t is equal to 0 in this equation, this will become v of 1 is equal to 0.7 into v of 0 plus 0.5 p into R0 minus W0. Similarly, substitute t is equal to 1. We will get v2 of t. v2 is equal to 0.7 into, this will become v1. So v1 whole value of this 0.7 into v0 plus 0.5 p R0 minus W0 plus 0.5 p R0 minus W0. Now simplifying this, you will get this thing 0.7 into 0.7 into V0. So this is the thing we have taken common, and then this thing. So we'll get this expression after simplification. We will get this expression after simplification. Okay. So now further simplification, if you see here that for we have find the value for t is equal to 0, for t is equal to 1, and then generalizing it for v of t. So 0, 1, 2, so t will become 0.7. So as you can see that for 2 we have 2.7, so this will become 0.7 raised to power t into v of naught, and then for v2 we just have 1, so we need to write 0.7 t minus 1, 0.7 t minus 2 up to 1. And then finally we have this thing. So this equation will become, on the basis of this equation, the coefficients. So what happens? The coefficients of Vt, so this, the coefficient of this Vt determines the rate of decay of V0. So on the basis of Vt, we can tell at what rate the V0 will decay. So V0 is basically what? V0 is our initial speed. So on the basis of this 0.7 we can tell at what rate our speed will decay. So if we have the bound between 1 and minus 1, for example, if the coefficients are greater than 1 or less than minus 1, Vt will grow out of bound. So this Vt will go out of bound, and you can check this out by putting the values here and find out. Or if this coefficient is less than 0, v of t will oscillate. This will always oscillate. Okay. So this is how you can determine the performance of the controller. So in this slide we will talk about our second example, that is designing closed loop control system. We can reduce the speed error caused by disturbances like grade or wind by enabling the controller to detect speed error and correct for them. To detect speed errors, we introduce a speed sensor in the system as shown in the figure. So this is our speed sensor which we are introducing. So previously in open loop system we do not have any sensor for the feedback. To measure the car speed, we also introduce a device that outputs the difference between the desired R of t. So our desired R of t is this speed. This is our R of t. and the actual speed is v of t. So what we have to do, what we are doing here, we are taking the difference of this actual speed minus our desired speed. So this error is r of t minus v of t. Note that the penalties for this closed loop approach are the cost of the sensor. So what's the disadvantage of this approach is that we have to pay extra for this sensor. We have to add complexity to controller. We are adding this complexity and the addition of sensor noise. So obviously this sensor will produce some noise. The benefit will be ability to change the rate of response, reduction of sensitivity to disturbances. So by using this feedback we can reduce the rate of the sensitivity, reduction of the sensitivity to model error, if we select the form of the controller to be linear and proportional. So if you look at the previous car model, we have v of t plus 1 is equal to 0.7 vt plus 0.5 u of t minus w of t. This w of t is our road grade or disturbance, and this u of t is controller input. So for linear controller, we have control law u of t is equal to p into r of t. So if we put u of t here, it will become 0.7 v of t plus 0.5 p r of t. Whereas in the case of closed loop, we have the same car model. However, the control law, in this case, we do not have like proportionality multiplying with the input. Rather, we have e of t. So e of t is equal to what? R of t minus v of t. So proportional is multiplying with r of t minus v of t. So we are going to put this u of t here in this equation. So it will become 0.7 minus 0.5 p into v of t plus 0.5 p rt minus w of t. So our system model has changed now because of the introduction of the sensor and with the introduction of the error detector. So now it has become a bit difficult, but somehow the system is very simple, so it won't look as difficult as for a bigger system. So let's move on to next slide. So in this slide we are going to talk about the stability, because we are dealing with the closed loop system, so we can define the stability constraint for this control. So as you know that u of t is equal to p into e of t, where e of t is equal to r of t minus v of t. So if I substitute this u of t in the system model, in the plant model, I will get v of t plus 1 is equal to 0.5 v of t plus 0.5 u of t minus w of t. After simplification, I will get this equation. Okay. So further simplification of this equation, you will get this. So in order for doing the same thing, first of all evaluate this equation for t is equal to 0, then evaluate this equation for v is equal to 1, then finally write the generalized form. So this is for v of t. So you need to find for v of 1, you need to find for v of 2, then you need to find out for v of t. Okay, so you can generalize it. As we have seen in our previous case that the coefficient of v of t, so this is the coefficient. Okay, so this coefficient will determine the stability because it has power t. So it will define whether the signal is it going to be growing, or is it going to be like exponentially growing or exponentially decaying, or it is oscillating. So what happens, we need to keep this magnitude less than 1 for stability. So whatever the value here we have with v naught, we need to keep this less than 1. So if you simplify it, and what you will get after simplification, so removing the mod sign, it means that between minus 1 and 1. So if you subtract minus 0.7 from both sides, we will get p between minus 0.6 and p between 3.4. If we keep the value of proportional to be this, our controller is going to remain stable and it will converge. Converges mean that we will reach to our desired R of t. Okay, so what we have to do after system model, we have to find out V0, the initial one, V1, then you can find out V2 if you want to, and then you have to generalize. So this is the generalized equation. You can see that t minus 1, t minus 2, then this is kind of a last expression, this one, and then finally we have 0.5 into this thing. Okay, so here we can find out the stability of our system. So let's move on to next slide. So in previous slide we have seen that our P, the stability for P was minus 0.6 to 3.4. We could set P close to 3.4 to obtain the fastest decay of the initial condition. However, remember that a negative alpha that was minus 0.6 will cause oscillation, which is something we would usually like to avoid. To keep alpha positives, so that we don't want to have P between minus 0.6 and 3.4. To avoid this, we will reduce the initial condition. So we want to keep this value as small as possible. So how we can keep this value small as possible? If I put P is equal to 1.4 here, 1.4 into 0.5, this will become 0. So I want to make this condition 0. I want to make this 0. Okay. So at P is equal to 1.4, the fastest rate of convergence to steady state without oscillation. So this is the best condition that we can find out. In this condition, this lies between minus 0.6 and 3.4, because at minus 0.6 we were getting oscillation, and at 3.4 the rate of decay was too fast. So we have the best possible condition, that is 1.4. So let's move on to next slide. So in previous slide we have seen that for what value of P we can have minimum oscillations and we can have a fast rate. However, in every condition we want this zero point 0.7 minus 0.5 P to be positive in order to avoid oscillation. So for this to be positive, we want P to be less than or equal to 1.4. So for this particular case, we will have an accurate control law or the control system. So let's move on to next slide and see the results. So now this is the third case of perfect tracking. Previously we have talked about, like, and if you do not want oscillation, we want P to be less than 1.4. So if we want to avoid the effect of V0, we will have uh, P between minus 0.6 and 3.4. Here if you want to have perfect tracking, so this is our control law. U of t is equal to P into R t minus Vt. So this is our system model. So for steady state condition, we want this Vt and V of t plus 1 VSS. So both of these are equal. In steady state, our current speed will be equal to our next speed. So if you solve for VSS, we can get this VSS is equal to this thing. So to make VSS as close as to R0 as possible, so if this is equal to this R0, what we have to do, we have to make this P very large. So for perfect tracking, we must need to make P very large. So we know that the maximum value of P can have is less than 3.4, because so what we can do, we can choose value of P near to 3.4. So for perfect tracking, we must need to have P very large. So let's move on to next slide. So this is our closed loop design. This is our V of t, and finally setting P is equal to 3.3. We know that for P 3.3 we are going to have no oscillations or some oscillation, because this value is quite high, but this is not a negative value. We are going to have a stable system, as we have already done the maths, and this will track well, and this will have perfect tracking. So just substituting the value of 3.3 and then check out how it works. So let's move on to next slide. So similarly, as in the case of open loop, we have analyzed the controller. Here we are going to analyze the controller. We have ignored the disturbance. Our desired speed is 50 miles per hour, whereas our initial speed is 20 miles per hour. So this is our system model. So this system model reduced to 0 0.7 V of t plus 0.5 and p is 3.3 and 50 minus V of t. So V of t is currently 20. So, and this is our control law, which we have substituting here, 3.3 into 50 minus V of t. You must need to make sure that u of t range from 0 to 45. This should not exceed 0 to 45 because our throttle angle is between 0 and 45. If this goes out, here you can see that our u of t is getting out of the limit. It's getting 99, it's getting minus 45, 91 and so on. Okay, so that's why our desired space is never getting to the 50. It's going to 20, then getting 63, then coming back to 22, 61. So it's always oscillating. So controller saturates. So here you can see it goes to 99. What we need to do, we need to limit it to 45. So this is what we have find out in the analysis, that our control output is getting out of limit. We can have only 0 degree to 45 degree of the throttle angle, which is u of t. So let's move on to next slide and see how we can solve this out. So in this slide we are going to saturate our controller. We're going to saturate our u of t if it goes beyond this range 0 and 45. So there will be a bad effect of the oscillation. This will cause oscillation. However, our controller will not go beyond the limit. So here you can see that without saturation at 20 miles per hour, our controller is getting the input of, or exerting the input of 99, which is not right. Okay, so what we can do, we can saturate it to 45. Okay, so without the saturation, in next step we were having the speed of 63.50 and we have the control input of minus 44, whereas with saturation we have next speed of 36.5 and our control input is 44.5. So we can see that after like steady state, this is 42.31 and this is 42.31. So there's no much difference between the steady state speeds, though we want our speed to be near to 50 miles per hour. However, we can see that we are not, here we are going out of the range. This value is going out of the range, this value is going out of the range, this value is going out of the range. Here we have all the values between 0 and 45. So let's move on to next slide and see how we can further improve our steady state error. So in order to avoid the oscillation, previously we were using the value of P to be 3.3. So we know that we have lots of oscillation, 20, 63, 22, 61. So there is up and down. And then we limit our controller to saturation. There were still 20, 36, 47, 37, lots of oscillation. So what we can do, we can set our P to be 1, so it will slow down. So now the tracking will slow down. So here you can see that we have improved the oscillation 20, 29, 30, 31, 31, 31, 31.25. However, the disadvantage of this slowing down is that we have a very large steady state error. We want to get to 50. We want to get to 50, but we are getting to 31. Previously we were getting to 42.31. So this is not good. So let's see how we can solve this problem as well in our next slide. So here in this slide we can have two analysis for P equal to 3.3 and P is equal to 1.0. Here you can see that for P is equal to 1.3 our response is very fast. However, there are oscillations here. so we are oscillating. Whereas for p equal to 1, our response is very slow and it gets into steady state very quickly and there are no oscillation. However, we want to reach to 50. We want to reach to 50, so there is a huge steady state error. Okay, so this is how we analyze for two different values of p's. So let's move on to next slide. So in this slide we will talk about minimize the effect of disturbance. The motivation for using closed loop control was to reduce the speed error caused by disturbances like grade. So if you look at the table, this shows the effect of plus 5% and minus 5%. So this is plus 5% of disturbance and this is minus 5% of disturbance. So this is our model v of t and this whole is our model. So we are substituting this w. So the value of w is in one case is minus 5 and in other case is plus 5. So for minus case, this is what we get, the speed. So this is for the value of p is equal to 3.3. So for p 3.3 we are getting to the final speed of 44.87 and for p w is equal to plus 5 we are getting at the speed of 39. So 39.74 is close to 42.31 as we have seen in our previous case. It is better than 33 and it's better than 66. So the trade-off using this disturbance in the model is that it will increase steady state error. So we have seen that our steady state error was previously almost 8, which has increased to 11 here. And obviously we will have oscillation because we are using p is equal to 3.3. So that was all for today. Rest of the thing we will see in next chapter.